Hi, boys and girls. All right, so today's video is a lesson about Newton's first law of inertia, which we talked about a little bit in our overview video on Monday and Tuesday. And so the best way I think for us to do this is just to go ahead and start watching the study jam together on Newton's first law.
Hey, can you give me a hand?
Nah,
Oh, RJ, this sofa's heavy. Can you help me move it?
I'm reading something. Can't we do it later?
Man, talk about inertia.
Inertia? What do you mean? I'm just chilling.
More like frozen in place. A perfect example, since inertia has to do with how things move. Or don't. It's Isaac Newton's first law of motion. The first part says that because of inertia, objects in motion will keep moving at the same speed in the same direction.
Forever?
Yep. Unless some force changes their motion.
Come on.
Which is really kind of crazy that objects would keep on moving forever, right? How did Sir Isaac Newton figure this out? I've always wondered, what experiments did he conduct to be able to figure this out?
How can something keep moving forever?
Well, think about Mia on her scooter. Once she starts rolling, she just keeps on going.
Yeah, until she runs into some gravel or something.
That's because gravel causes friction. It makes her slow down and stop.
Yeah, but she would have stopped eventually.
Not if there wasn't any friction or another force to stop her.
Which I feel like I need to stop and say something about that. Of course, on Earth, there will always be a force that will stop you because there is matter all around us. And friction is when matter rubs against matter. So if you were the girl on the scooter, you probably would have come to a stop before you got to the gravel, because you may even have been thinking about that. Like, I might have stopped before with just one push, right? Because you have other forces that are causing other things that are causing friction too. The air that's all around you will slow your scooter down, and also the rubbing up against the ground will slow it down too. Now, of course, when the scooter hits the sand or the gravel, that has way more friction than nice smooth concrete, so it will slow you down really, really fast. This always makes me think of the highways. If you've ever traveled north on I-77 through Virginia, there are mountains, and when you're coming through the mountains, it's always super freaky for me as I'm coming down the mountain, and you can see on the side of the mountain a path that goes up the mountain that's full of sand, and those are for runaway semi trucks. If a semi truck's brakes die and they're going zooming down the mountain, they can always pull into that ramp that goes up, and it's full of sand, and it would stop the truck. But even so, I would be so scared if that happened to me. All right, let's keep going.
That's the most important part of Newton's law. If Mia was zipping along in outer space where there's no friction, once she started moving, she wouldn't need another force or push to keep her moving. She'd just keep going at the same velocity forever.
Velocity? Isn't that like speed?
Well, speed and direction.
Wow. Can you imagine Mia going straight out into space?
Now that would be a trip. Speaking of trips, inertia is what makes you slide sideways when you're riding in a car that makes a sharp...
Okay, let's stop there for just a second, because I would like to talk to you about velocity. Velocity is a word that I'm going to want you to make a note about. So I'm going to keep my notebook right here. Velocity is speed, and it also includes the direction that you're traveling. So mostly we just think about speed. Now, if you were trying to tell someone how fast you were going, then you would usually say something like 50 miles per hour, miles per hour. The thing about speed is there's a formula for it. In order to calculate the speed of something, you would have the speed, and you would have to divide the distance. See right there, miles, that's distance. And you would have to divide it by the time. See, hours is the time. So every time, you haven't even really realized this, but every time you've seen the speed limit sign on the highway where it says 20 miles per hour, or 30 or 40 or 50 or 60 or 70 miles per hour, is really a fraction right there. Speed equals distance divided by time. And you know this from math already, that when you have a fraction, the numerator is really a division problem, dividing the numerator by the denominator, right? You can also do the speed formula like this. Speed equals distance divided by time if you want to, but scientists usually write it out like this as a fraction. So for instance, if let's see, I was traveling and I traveled 100 miles, and in that 100 miles, it took me 4 hours, right? Then in order to find the speed that I was going, I would have to do the distance divided by the 4 hours. So it would be 100 divided by 4, 4 times, okay, so 4 times 100 is 25 because 25 is 4 quarters. So my speed limit would have been 25 miles per hour, right? And a lot of times in science, you will write it like this and just write it like a slash, like a fraction. All right, now that's all for speed, right? And we'll go over this again later. But if you're actually talking about the velocity of something, then you would have to be saying for the amount of speed, my speed or slash to get my velocity, I would say my speed, which is 25 miles per hour, and I would also say the direction I'm going. So let's say I was going southwest. So in order to do velocity, right, you're doing the speed plus the direction traveled. All right, pretty cool. Or not, but even so, it's something I bet you didn't know. Ha ha. All right, let's go back over here to the video and play.
Sharp turn.
Really?
Oh, yeah. When you're driving along, even though you don't feel it, your body's moving as fast and in the same direction as the car. If the car turns fast, your body keeps moving in the direction you were going before the turn. So if you're turning left, you'll slide to the right. See?
That's wild. I think I'm getting it. But what about the sofa? You said it has inertia, but how?
Okay, so let's stop where they were just saying. Now, a really classic example of inertia is if you're driving on the car and your mom or your dad slams on the brakes to keep from hitting something, what happens to your head when they hit the brakes? Right? Right? Doesn't it go like this and then come back like that? In fact, that's actually a medical condition called whiplash. So someone slams on the brakes, right? And your head goes whoosh. All right. Well, what's really happening is that your body is going at the same speed as the car. When your parent hits the brake, your body has not had any force applied to it. Only the car has. The brake applied a friction force that slowed your car down, but your body didn't have any force applied to it. So your body is acting in inertia. In other words, it wants to keep going because your car was going. Now, a lot of times, if someone slams on the brake, what is the force that makes you keep from flying out of the windshield? Your seatbelt, or you might even hit the glass and bang your head, right? Because your body keeps going until a force is applied, the force of the seatbelt or the force of smashing into the windshield. So here's a little safety lesson. Always wear your seatbelt because of inertia. Your body's going to want to keep flying while the car stops from the brakes. Inertia.
It's standing still.
Yeah, and so's the scooter after it stops. Lucky for us, Newton discovered that the same rules work for all objects. So part 2 of Newton's first law says that because of inertia, objects at rest will stay at rest unless a force makes them move.
What kind of force?
Well, Mia can push off with her foot to get enough force to start moving again.
So how come you couldn't make the sofa move?
Well, the heavier things are, the more inertia they have.
And remember, well, actually, I haven't said this to you guys yet. I don't like to say heavy in science. I like to say more massive. That's a better scientific term. The more massive something is, the more inertia it has. Now let's think about that again. And this is an example I always use. If you were trying to push an elephant, it would be way more difficult to push an elephant than, let's say, I don't know, a mouse. You would push and push and push on your elephant, just like me is pushing on the couch, and your elephant probably wouldn't move unless it just wanted to, but not because you applied force to it. So something with more mass has more inertia and needs more force in order to make it move. You feel me? All right.
And the harder it is to make them move.
That sofa is really heavy.
That's why I needed your help?
Yeah, I get you. So let's go over this inertia thing again. I want to be sure I've got it. Newton's first law of motion says that because of inertia, objects in motion will keep moving at the same velocity, that's speed and direction, and objects at rest will stay at rest, unless a force changes things. Friction is one kind of force. It can make a moving object slow down or stop. Heavier objects are harder to move or stop because they have more inertia.
Impressive, RJ. I think you got inertia down.
Thanks. Now, how about I get over it and help you move that heavy thing?
Well, I don't want to force you, but I'd love it.
Oh, these study jams just kill me. All right. Love you. See y'all later.